Welcome to Section 5. Section 5, we're going to be learning some smaller applications of derivatives. The first of these being linearization. So if I were to ask you, we have some function that I'm calling f of x, and I want to find the tangent at x equals a. Well, we would need a point, and the point would be going through a f of a. And the slope would be at f prime of a. So our tangent would be y minus f of a equals f prime of a times x minus a in point slope form. Well, linearization is the idea of using this tangent equation at x equals a to estimate values for f of x when x is close to a. And the idea of this is if I say this is my function f, and here is a for an x value, the tangent looks like this. And linearization is saying that as long as I'm close to this point here, there's not much difference between the actual f value and the tangent value. Or if I go a little bit over this side, the actual f value, the tangent value. They're very close together. Now, as I move further away, say here, there's a much larger difference. But at the point of tangency, or close to the point of tangency, as far as estimates go, it's a good estimate. So, for example, if I wanted to find the linearization for cosine of x at pi over 2, all that's really asking is what's the tangent. So I need a point, which would be at pi over 2, and then plug that in. Cosine of pi over 2 is 0. Then to find the slope of the tangent, I need the derivative of f, which would be negative sine of x. And the derivative at pi over 2 would be negative 1. So the equation for my tangent would be y minus 0 equals negative 1 times quantity x minus pi over 2. And I can now use this to make estimates. So pi over 2 is about 1.57. So if I wanted to estimate the cosine of 1.6, that's pretty close to pi over 2, so I can actually just go ahead and plug that into my tangent and say that y minus 0 is going to be equal to the negative of 1.6 minus pi over 2. Or I should say it's going to be about that, which is going to be about negative 0.03. And if you type that in your calculator, you should find that that is close. In fact, we actually see that that cosine of 1.6 is about negative 0.029. So that's a pretty good estimate, pretty quick as well, instead of having to know how to find the cosine of 1.6 without a calculator. Another way here is so if I wanted to find a linearization of f at x equals 3 when f is square root of 1.6, or 1 plus x, that's the same as 1 plus x all raised to the 1/2 power. Well, I need a point, so when x is 3, plug that into f. Y would be 2. For the slope, I need derivative of f, which would be 1/2 of 1 plus x to the negative 1/2 times derivative of the inside, which is just 1. That'd be 1 over 2 square root of 1 plus x. And then derivative at 3 would be 1/4. So my linearization is my tangent, so y minus 2 is equal to 1/4 times x minus 3. Now, where something like this can come in handy is, let's say you wanted to use linearizations to approximate roots. So first, if we look at the square root of 123, the key here is getting an idea of what you should center your linearization around. In other words, what should you use as a for your point of tangency? And you want to pick something that's close. So here, the square root of 123, well, that's close to the square root of 121. So if I say that my function is the square root of x, well then I'm going to use an x value of 121, which would give me a y value of 11 when I plug that into this function. Derivative of the square root of x would be 1 over 2 square root of x. So the derivative at, oops. So my derivative when x is 121 would be 1 over 22. So a linearization would be y minus 11 is equal to 1 over 22 times x minus 121. Well then, if I want to estimate the square root of 123, I would plug 123 in for x in my linearization, and I would get y minus 11 equals 1 over 22. So y would be about, or I should say the square root of 123 would be about 11 and 1/11 when I solve this linearization for y. If I were doing it with the cube root of 123, well again, the idea would be that my function would be the cube root of x. As far as what I would use as a point of tangency here, I would want to pick something where I have close to a perfect cube. Well, 125 is a perfect cube. That's close to 123. And if I plug 120, find the cube root of 125, that would be 5. Well, then I need my derivative here, which would be 1 over 3 times the cube root of x squared. And so my derivative at 125 would be 1 over 75. So my linearization would be y minus 5 equals 1 over 75, x minus 125. And then to estimate the cube root of 123, I could just plug 123 in for x. So y minus 5 is 1 over 75 times 123 minus 125. And solving that for y, I would get that the cube root of 123 is about minus 2 75ths, which is about 4 and 73/75. Just caught a small error in my writing here, actually. That should be 123.